go for live. All right, so I'm start now. Okay, I'm sorry. All right, let's I go. Wait. All right. Okay. My. All right. So actually, all right. Let's restart. Okay. Go for. All right. So now my question. Okay. Let's we go. My question here. What is the difference between solving ordinary differential equation and partial differential equation? This is my first question. All right. What is different between ordinary differential equation and partial differential equation? You can answer this question through the top chat. All right. So thank you very much, Salwa. All right. Pa, Akmal, Purani, Lo, all right, and then Zurin, Loy, Desmond, Nur Hanian, Tiong, Fatana, Nur Shahira, Muhammad Arif, Shifa, Hazira, Erin, Nurul, Khairulisa, right, Ko, Alia, okay, Lo, Nur Saidatul, Aziza, alright, Ain, Tan, Emilia, okay, Shannon, right, Nurin again, alright, Faiza, Nur, Siti Nur, Sabrina, Hani, alright, and then Nasri, Chin, Nur Shafika, Mas, and then Nur Zara, Purani, all right, Nur Nabiha, all right, Siti Aisha, all right, the first Salwa, all right. So these all the students, okay, who are registered at the YouTube, all right. So now let's we ask you a question. The question here, what is the difference between, okay, what is different between ordinary differential equation and partial differential equation? All right, my question you need to answer. Okay, solving ordinary differential equation, you need to use what? You need to use Rajkata method, all right? You need to use Taylor's method and Euler method. And then the ordinary is depend on one parameter, y respect to x, okay? U respect to x, okay? One parameter only, all right? However, PDE, partial differential equation, is based on the 2D. For example, the solution for parabolic equation, hyperbolic equation, elliptic equation is a 2D, x and y. X and T, all right, Y and T, all right. So it's depend on the two parameters. That's why your answer is a slice, okay, of the graph, wave graph, all right. So now I want to share with you, okay, I want to share with you the PDF file. Okay, let's I go to the PDF file. If I can share with you chapter 9. Okay, go to the chapter 9, go to your e-content. Okay, I stop here. All right, so I think you can see, okay, now, all right, am I right? You can see my lecture now. I'm waiting for you to register at the YouTube actually. Now, I want to share with you um, my PDF files. Let's you go to the PDF file. Okay, now this is a PDF file. All right, so I want you to focus on example 9.1. Okay, let's we go to the true how to let's we focus in example 9.1. In 9.1, okay, I already stated here, okay, the del u is del squared u over del x squared plus del squared u over del y squared equal to x exponent y, where x is between 0 and 2 and y is between 0 and 1. And then there is a four condition. Okay, the first condition, second condition, third condition, and fourth condition. The first condition is when x equal to 0. And then when x equal to 2, meaning that the last grid. And then the third condition is y equal to 0 and y equal to 1. Okay, the last point. And then delta x and delta y is equal, is 0.5. So delta x divided by delta y is equal to 1. All right, we already know. And then we want to solve the discretization of Poisson equation. We are using chapter 5. And then we solve the linear system using Gauss-Seidel. All right. So now, the first thing you need to convert is from the boundary condition to an initial condition to the graph here. You can see graph here. All right. It's very, very, very clear. Okay. What is the clear? The clear is we have a boundary condition. Boundary condition when x equal to 2, okay, when I equal to 4, all right, so we can get u equal to 2 exponent yj. And then the next is when x equal to 0, y is moving from y equal to 0 up to yn. Okay, the graph is on your left hand side. All right, and then the next is when x equal to x and then y is equal to 0, the last, okay, the first point here. And then the last point here is when x equal to x and y is equal to 1. Okay, means that j is equal to 2. All right, because we have 2 time step here. All right, the way how to discretize, okay, the second step is you need to apply chapter 4. All right, you can see here the first derivative, the second derivative respect to y, you can discretize using this. Okay, ui plus 1 and then plus ui minus 1. You just change I. And then this one you just change y. It's a j plus 1. You change j minus 1 here. J plus 1 and j minus 1. This is applying 5.5 in chapter 5. Change respect to y. And then this part is change respect to x. All right. So when you do the discretization, bring the last part of your discretization in star function. How to get star? Okay, you have collect all the parameter for uij minus 1, uij plus 1, ui minus 1, and ui plus 1. All right, you collect. You have 5 points. However, because you have initial value, u11, u12, all right, boundary. Where is the boundary? At the corners here, you have a value. So you create actually not 5.5 matrix, because this one is look like you have 5 grid, 1, 2, 3, 4, 5. You can see here, these are 5 grid. Actually, when we have a corners, the marks, the value at the corners, here, so you will create 3 by 3 matrix. All right. So you have a value at the corners here. All right. And then corners here. All right. So you will create a 3 by 3 matrix. Okay. Or 2 by 2 matrix, because there is a value at the corners. Okay. You have to know there is a value at the corners. Replace when you want to find u11, is depend on u12, u01, u10. All the corners 10, u01, okay, here, and then u12 here, all is the corners. So you just find these 2 grid. All right, okay. How about this one? You want to find u21. U21 is depend on u22. This where I structured the grid for Poisson equation. So u21, u22, and u20 is given in the boundary. So you just find the 3 grid here: u11, u21, and u31. To get u31, all right, you need to know the value for u32, u41, and u30. All right, all at the boundary. You can get from the data given in the question. Okay, so now you need to just use u21 and u31. So in terms of the process of discretization here, be careful at the corners. Where you want to be careful at the corners. Alright. So towards the end, it's not 5 by 5. Your matrix is a 3 by 3 because all the values at the corners you replace with a number. Alright. So now I want to start my process of discretization using the way how you write. I want to teach you how to make the process of discretization very, very fast. Very, very fast. All right. So now let's focus. Stop sharing. I want to focus my screen here. All right. How to discretize the boundary partial diffusion equation using elliptic equation. Yeah. All right. So I think okay. I sharing. Am I right? I'm sharing. Now I'm sharing. All right. So the question here is how to discretize the elliptic equation. Again, many times I focus, is to do the process of discretization for del squared u over del x squared. So you do the chapter 5. You go to chapter 5 and then here you can see ui minus 1, ui plus 1 divided by delta x squared. All right. And then I relieve J first. And then now I want to discretize second order derivative respect to y. I will get uj plus 1 minus 2 ui uj plus uj plus 1. All right. So now I insert the value of I and j letter. All right. Xi exponent yj is a common. When you meet x, you need to put I, and then when you meet j, you need to put yj. All right. So now I insert I and j. You can see here, I insert I and j. Okay, j is maintained for discretize the uxx, and I is maintained when you want to discretize respect to y. All right. So you can see here now your discretization is based on the uij. Okay, ui minus 1, uij, ui minus plus 1j. All right. So you times delta x for every both part because you want to make it more simple. And then in this case, delta x and delta y is similar. Lambda is equal to 1. So you put in the group the 5 point. Where is the 5 point? ui minus 1j, ui plus 1j, uij minus 1, and uij plus 1. All right. You are developing 5 point of the Poisson equation. All right. Now, when you block, when you put in the group, be careful because your lambda, the delta x is equal to 0.5 divided by 0.5 is equal to 1. And then you be careful because the x is moving from 0.5, 1.0, 1.5. Right? The y is start from 0, 0.5, and 1.0. All right. Now put all the values. All right. And then you can get the star function based on the 5-point discretization. However, since you have the boundary and initial condition, so you're not solving 5.5, you're solving 3 by 3 because the corners, j minus 1 and j plus 1, the corners, is given in the boundary condition. All right. And then j and then I plus 1 and I minus 1 at the corners, some point is given in the question. That's why you will generate 3 by 3 matrix. All right. You will generate 3 by 3. All right. Why? Because j plus 1 and j minus 1 at the corners, at the boundary, at the last boundary. All right. And the early boundary. All right. So now, don't say that, you solve this problem simple, not simple, it's really simple. You can downgrade the process of calculation from 5 point to 3 point, because you have the boundary condition and initial condition. All right. So this is my question. All right. So my question here. Okay. Can you go to the my question here? All right. How to discretize Poisson equation? Okay, what is the process you do when you want to solve the Poisson equation? Right, so this is my question. Okay, you can answer my question. How to discretize Poisson equation? Right, we already learned in chapter 5, all right, about the discretization second order derivative 5.11. I'm using 5.11 to do the discretion respect to x and respect to y. Okay? All right. So you can answer my question. Okay, now, okay, I stop sharing. I want to share now, okay, the detail how to do the discretization of Poisson equation using finite different method. Okay, using finite different method. Okay, to do this, okay, be careful because you have 3 points to find. Go to page, come on. Come on, you go to page chapter 9. Okay, I'm using example 9 point. I'm using 9.1. Okay, I'm using example 9.1. So be careful when you do the discretization. All right, you can see here there is 3 points you need to find. What is a 3 point? I equal to 1, j equal to 1, I equal to 2, j equal to 2, and I equal to 3, j equal to 1. All right. So now, for the first one, I equal to 1, j equal to 1. Okay, you can meet, okay, 1, 0, 0, 1. You can meet this grid, and then 1, 2. So meaning that all this point is the boundary condition. Is a boundary condition, right? So now, my question is how to discretize the problem. How to discretize the problem. So be careful when you do the discretization process. All right. So put the value, okay, at the corners 1, 2. Okay, when y is equal, j is equal to 2 at the corners up there. So you can replace the value. The value is a x exponent. All right. So you can get the value is 1.359, all right, and then u 0, 001 is 0, and u10 is 0.5. You can get 2 points here, all right, because all the rest is a real number put on your right hand side, all right. You can get negative 4 u11 plus u21 equal to negative 1.653. And then now you generate when I equal to 2 and j is equal to 1. Your time step, your y is always j equal to 1. J equal to 2 and j equal to 0 is a boundary. All right, you can get the value. So when I equal to 2, j equal to 1, you also have a boundary. Okay, it's a u20 and u22. u20, you will use u20 is xi. Xi is x. Xi, I is 2, is 1, all right, and then the other one u22 at the last, okay, the last interval is a 2.718, okay, is a xi exponent. Yeah, so be careful. This will bring you a real number and put on your right hand side. So you downgrade from 5 point to 3 point. You downgrade from 5 point to 3 point. For the next, okay, last point is when I equal to 3, j equal to 1. We want to find the wave when I equal to 3, j equal to 1 at the middle. So it depends on the u30, and then it also depends on the u32, all right, u32, all right, and then the value on your right hand side, you bring, okay, all the value on the right hand side, you will get u21 minus 4u31. The rest is a boundary. Okay, the rest value at the boundary put on the right hand side. So now This is a process. The third process is to convert the linear system to the matrix form. You learn in chapter 2 how you convert from the linear system of equation to the matrix form. The matrix form here is a 3 by 3. So you can see here, this is the first equation, second equation, and the third equation. It's all referred from the star function, right? So the last equation is a 2 point. The second equation is 3 point. The first equation is a 2 point. All is a diagonal matrix for matrix AX equal to F, all right? How many matrix? How many linear system you got? 3 by 3. So the linear system that you want to form in matrix is also 3 by 3. U11, U21, and U31 equal to negative 1.563, negative 3.306, and negative 8256. All right. The matrix A is a 3 by 3. The element is always stated 1, negative 4, 1. All right. The diagonal, okay, we call this one is a diagonal matrix, always using negative 4, 1, and 1. Right. We can solve this linear system using Gauss-Seidel method. You can use the direct method, for example, Thomas algorithm. So please go to chapter 2. Find the Thomas algorithm. All right. Instead of the Gauss-Seidel method, all right? To do the Gauss-Seidel method, yes, it's very complicated because the element now is a 3 element. U11, the wave value, U21, and U31, right? So the element of the wave will be stored when all the previous value of U11, U21, and U31 minus the new value of U11, U21, and U31 is less than epsilon. Is less than epsilon. All right. So this is what you need to focus. Okay. Make sure to terminate from the iteration. All the points should be less than epsilon. All right. So you will get the 3 point of the wave. When x equal to 0.5, y equal to 0.5. When x equal to 1, y equal to 0.5. When x equal to 1.5, y equal to 0.5. All right. So you have a 3 point for the wave stage y equal to 0.5 is a y1. And then x is moving from I equal to 1, I equal to 2, and I equal to 3. So when you draw the value from the linear system using Gauss-Seidel, the graph is a curve. There is a piece of graph which is a curve, all right? So this is what we do, okay? What we do. All right, so now I hope that you can answer the question how to, so this my good. Okay, the answer is good. You are using finite different method. All right. So the tree process. What is a tree process? To solve elliptic equation, or sometimes I say Poisson equation. Okay. What is the first step? Equation. All right. So now my question is, what is the step to solve the elliptic equation? The first is, all right, find the boundary condition and initial condition for the elliptic equation. The second is discretize using finite different method, second order derivative, chapter 4, 5.11. Right? Put, okay, for every time step, for every grid, j equal to 1, I equal to 1, 2, 3. All right. The third step, convert the linear system to matrix. If the matrix 5.5, because of there is a value at the initial and boundary condition, they will downgrade to 3 by 3 matrix. you can solve using Thomas algorithm, not Thomas method, Thomas algorithm. Find very fast where the Thomas algorithm, go to the chapter 2 and go to page 58. Go to page 58 from your books on e-notes. All right. So you can see here. All right. So the last process you solve using Thomas algorithm. All right. I know you know what is a Thomas method by differentiate between L and U. After getting L and U, all right, after getting D1, all right, and then you know what is B1, all right, so you just insert in the Thomas algorithm in page 58, all right, in page 58, all right. So there is a three step to solve the Poisson equation. Okay, now I want to share with you how to solve a problem if the problem is a hyperbolic equation. Hyperbolic equation. What is the difference between elliptic and hyperbolic? So now I'm stop sharing. I want to go to the PDF file. Okay, now I go to the PDF file. So you have to know that what is an elliptic equation. Okay, go to the exercise here. All the elliptic equation is a plus. Okay, you can see here is a plus. All right. I want to focus to my notes. Okay, all here del squared u over del squared u over del x squared plus del squared u over divided by dy squared equal to 0. This one is a Laplace. It's a one type of the elliptic, but plus. Okay, is a plus. All right. But now I want you to focus to the all plus. The process similar. If you go to the exercise, all plus elliptic, okay, all plus del squared y, okay, all plus, okay, the answer is all plus. The boundary condition I change to make sure there is a variety of the question. I change the boundary to make sure this is a variety of question. Okay, you can see here I'm using cosinus and sinus, and then I'm also using for boundary condition. Okay, and then with a different lambda, okay, with a different pi. What is a pi? Pi is a value 3.14. All right, so now you need to press gradient, all right, to make sure that you can answer the parabolic correctly. When you go to the hyperbolic, why I need to go to hyperbolic? Because it's a similar terminology, similar process. Okay, however, dissimilar. However, I bring y on your right hand side. So you will get c squared del squared u over del x squared minus del squared u over del y squared. All right, minus. There is always negative here. Okay, minus here. Boundary, okay, and initial. You can see here there is a boundary condition and initial condition with derivative. This one you need to refer to chapter ODE. How I discretize the initial condition with the derivative. All right, I'm using formula 5.8, center different formula respect to y. In our case, is respect to t. All right. Okay, so you can see the wave, the hyperbolic is more on the vertical replacement. This is the wave from the string, the wave from the movement, water, air, okay, macro, okay, the wave, okay, so we are using hyperbolic. All right, so I want you to go to the, this problem, okay. Okay, the problem is I just bring y to right hand side, all right. So meaning that if I bring del squared u over t squared, there will be negative here on your right hand side. So that is a hyperbolic. That is a wave equation. All right. So the difference with the elliptic, the notation of the second term of equation is a positive or negative. The rest, no problem. Okay. You have How to write this one is a delta x is 0.2, delta t is a 0.1, x is between 0 and 1, and t is a between 0 and 0.2. Okay, 0 and 0.2. So the question here, they want you to find when x equal to 0 up to 0.1, 0.4, 0.6, 0.8, and 1.0, the t is only 2 time step. When t is equal to 0, t is equal to 0.1, and t is equal to 0.2. All right. However, when you put in the notation here, you can see, okay, how many conditions. When the first is when x equal to 0 and x equal to 1, the last corner, okay, x equal to 0 here and x equal to 1 is here. The last point is a boundary condition, all right? So you can put the value. The value is 0. All right, and then second, when y is equal to 0, so the the wave is 1 over 8 sine pi x. When y is equal to 0, where is the y equal to 0? This corner, okay, y is equal to 0, sorry. Y is equal to 0 is this corner, the last corner here, all right? This corner is a y equal to 0, all right, because they want you to find y equal to 0, okay, is equal to 1 over 8 sine pi. X is moving from 0.2, 0.4, 0.8, all right? And then the last is, there is no boundary at the last corner, where the last time step, all right? This is not boundary condition. So in this case, how many points you need to find? Okay, how many points? There is no value at the corners. You need to find the values in the boundary, in the region, is a 1, U11, U21, U31, U41. All right. X is moving from 1 to 4. And then you also need to find the boundary condition, the value of wave when t is equal to 0.2, the second time step. So you have to find 8 times 8, okay? 8 times 8 time step, all right? So you can see here, okay, that is not involved the, this one is a 5 point from the hyperbolic discretization using finite difference method. There is not involved Gauss-Seidel or elliptic because the result is a direct method. You can get direct method, okay? But how many points you need to do? 8 points. Where is the point? The point when t is equal to 0.1 and then t is equal to 0.2. You have to find 8 points. The way how you discretize is similar. You are applying, so just the notation different, but the rest is similar. Differentiate u respect to x, so you need to change I plus 1 and I minus 1 here. J is a maintain. There on your right hand side is a discretization second order respect to time. You need to change j plus 1 and j minus 1. Okay, here. The rest I is a maintain. All right. So now you have how many points now? You have, where is your star function? Your star function is here. It's based on the 5-point derivative. However, they will change to very simple formula because this is a direct method. It's not involve linear system. All right. So now we go to the how we discretize. This is my question is how to discretize the hyperbolic equation. So this is my question. Let's stop sharing. I'm really worried how you discretize the hyperbolic equation. So that's I'm worried, all right, because they will spend you a time to refer to chapter 4, 5.11. So now, okay, when you do a hyperbolic, okay, I want you to notice here, there is a minus. Okay, minus delta squared u over del y squared. In our case, is a t squared, all right? So the pattern we recognize already to make a difference with the with the Poisson equation, all right, with the elliptic equation, yeah, with the elliptic equation. All right, so now to do a finite different method, you need to replace, okay, as usual, from coordinate to the grid form, from uxy to uij. So when you do the second order derivative respect to y, you will get ui minus 1 minus 2ui plus ui plus 1 divided by delta x. And then on your right hand side, you just focus this second order discretization respect to y. So you will get uj minus 1, uj and uj plus 1 divided by delta y squared. All right, delta y squared. All right, so now, okay, how to group, okay, the parameter, because we have delta x squared here, delta y squared here, how to make it in group. So in this case, all right, you make sure that there is a 5-point involved. ui minus 1, uij, ui plus 1, and then uj minus 1, uj plus 1. All right, there is a 5-point. All right, put in the good notation. Since y is a time, okay, time, so you need to bring uij plus 1, the new time step on your right hand side. All right. However, before that, I do delta y for every both part, because delta y is a time. For example, delta y is a t, so it's time. So you will get delta is a delta y over delta x squared. All right. So in this case, delta x and delta y is similar or not? In our case, let's me go to the example hyperbolic equation. Okay, is if similar, so means that, all right, that lambda is equal to 1. All right, so now bring all the negative uij on your right hand side, and then uj plus 1 to your hand side. Why j plus 1? Because we always replace y to t, to time. So to get a new time step for the wave is depend on lambda ui minus 1j plus 2 1 minus lambda uij plus lambda ui plus 1j minus j minus 1. All right. So this, I hope you make sure improve yourself to this discretization. Okay, make it very fast. You need to discretize in 5 minutes. Okay, and then you need to know where is the point. The point is a 5-point, the same as elliptic. Okay, above, below, left, and right. Okay, almost 5-point. All right, but the right hand side is a uij plus 1, the new time step. All right, so now, since you are given the boundary condition, you put in boundary condition, and then you need to know that when I equal to 0, okay, j plus 1, okay, j is equal to 0, you will get 0, 1. Where is a 0, 1? At the boundary. And then when I equal to 2, j is equal to 0, you will get, okay, 2, 0, and so on. All right. So this is a way how you discretize the hyperbolic equation. All right. Be careful. Okay. Now, same as usual, how we discretize the hyperbolic equation. Be careful. We have 5 points, and then all the value is similar. So now, let's stop sharing. I want to solve the example of 9 point, let's we go, 9.5, page 253. 253, 9.5. How to discretize? So my question is how to discretize the hyperbolic equation. So this is my question. How to discretize the hyperbolic equation. Right? So I want you to understand the way is similar to elliptic, but negative for the second term, negative del squared u over del y squared. All right, or sometimes I put t. In the textbook, they put t. All right, so now I'm stop sharing. I want to discretize the hyperbolic equation for this example. All right, I put in bigger. Okay, I'm stop sharing here. I want to focus how to discretize the hyperbolic equation using wave. Okay, using wave equation. All right, so now we want to apply chapter 4, 5.1, second order derivative of partial diffusion equation. You apply for del squared u over del x squared. You apply del squared u over del y squared. X is between 0 and 1 and y is equal to greater than 0. But the size of delta x and delta y is equal to 0.5. All right, it's similar. So your lambda is always 1. Your lambda is always 1. All right, so now, okay, make sure you write carefully the boundary condition when x equal to 0, okay, u is equal to 0. When x equal to 1, u is equal to 0, all right? So you need to recognize where is the location for this grid, for this structure, all right? So now, initial condition is when y is equal to 0, okay, u is equal to 1 over 8 sine pi xi. So x is between 0 and 1, all right? So next is delta, okay? Delta squared u over delta x squared, okay? Okay, or you want to discretize delta squared u over del y squared when when t is equal to 0, right? So you need to discretize this one using 5.8 center different formula for first order derivative, all right? First order derivative when y is equal to 0. All right, so by using finite different method, okay, you know that delta x is a 0.2. Delta y is a 0.1. So your lambda is not equal to 1. It's different. It's depend on the how you do a delta y over delta x here. Your epsilon is 0.005 because you want to stop the iteration based on 4 decimal places. You are very lucky. They give you the exact solution, meaning that you can find the approximation solution from the exact solution. You can do the error between exact solution and approximation solution, right? So you always play around with this type of question in boundary value problem. So we are using the same process. The first process is what? I write here. The first step is what? You need to detect, notice the domain of your solution. Where is your solution using finite different method? Okay, in this case, you are given the initial and boundary condition. So n is a b minus a divided by delta x, is 1 minus 0 divided by 0.2 is a 5. And then the x now is a x0, x1, x2, x3, x4, x5. I hope you need to transform this problem, all right, to the grid form. M is a b minus a divided by delta y, is a b is a 1 minus 0 divided by 0.1. So you have a time step, 10 time step, but we focus on y0 and y1 when the y is equal to 0 and y equal to 1 and y equal to 2. All right. So now draw. Okay, you need to draw the graph. You know why? Because we want to know the location of domain for hyperbolic equation. Yeah, we want to find the domain. Where is the domain? Where is the boundary condition to reduce the calculation? Okay, to reduce the calculation of 5-point discretization. Okay, so you can see here boundary. Okay, there is a how many boundary? There is a 4 boundary here. At the corners equal to 0 when x equal to 0, and then x5 is equal to 2, is also will be u equal to 0. Alright, and then this is the first derivative, the first boundary condition, second boundary condition. All the boundary you have the value. Alright, the value is a 0, and then the second boundary the initial condition is when y equal to 0. Okay, when y equal to 0 or j is equal to 0. When j is equal to 0, you can get del u over del y equal to 0. So in this case, we are using 5.8 is a second order, is a first order derivative. So you put here is a uij equal to uij minus 1. Right? So when you have, I'm using backward different formula. I'm not using center different formula. Sorry, yeah. I'm using center different formula here. All right, please. This one should be ij plus 1. Yeah. So you will get that when I is moving and j is equal to -1, so we'll get ui and j is equal to 0. You will replace. When j is equal to -1, you replace j is equal to 1. J is equal to 1. So you can see here. All right. So we focus this boundary condition to find the value when j is a -1. You focus on j is -1. Step 2 is a discretize using finite different method. I know you quite expert using finite different method because you know how to discretize second order derivative respect to x. So I is moving, I plus 1 and I minus 1 equal to discretization on the second derivative respect to y. J is moving, j plus 1 and j minus 1. And then you put I, the letter. You put I and j, which is maintain the process of discretization in two-dimensional problem. In two-dimensional problem of partial diffusion equation. Yeah. Okay. So now the next step, okay, you already know we need to what? We need to put in the group. Okay, you times delta y, okay, every both part. Okay, square every both part. All right, you will get the discretization as the following, and then group the next step is a group the discretization. Let's we group. Okay, group ij plus 1, group ij, this is very important, group ij. All right, bring ij plus 1 on your right hand side because j is a time. The new time is depend on the previous time j. Put your right hand side. This is a hyperbolic because time. We want to focus on time. Right? Time. Okay, so the first step, the first time is a j plus 1 is above in the computational molecule is a very high time. Okay, j plus 1 is above molecule. All right, and then group, and then don't forget group into the computational molecule. Okay, in the computational molecule, j plus 1, j and j minus 1, I plus 1, I and I minus 1. There is always created 5-point discretization. All right. So the next is how to solve. So this is a very important step because we want to solve the hyperbolic. All right. So now let's share with you. I want you answer my question. How to discretize the hyperbolic is similar to the elliptic, but make sure that uij plus 1 on your right hand side because j is a depend on time. All right. Some question here is a depend on time. So the new j plus 1 is the above one. The computational molecule at the above point depends on the 4 point at the previous time step. All right. And then how to discretize is similar to the elliptic equation. However, okay, the solution is a direct method because it is straightforward because you have the value at the initial condition and boundary condition. All right. So now I want you to solve this problem. Okay. How to get the solution. the solution of uij, okay, ux and y. This one is my question, how to draw the graph of the hyperbolic, how to get the solution of the hyperbolic, how to draw the graph of the hyperbolic. All right, for the solution here, you need to find the first time step, j is equal to 1 and j is equal to 2. J is equal to 0 is a boundary condition, is an initial condition, is given in the question. You are going to apply. All right. So now, okay, my question here, how to get the solution for ij. All right. So now I want to stop sharing. I go to the material. Actually, I give the material to your Telegram. So it's not difficult, okay, to make sure, okay, you understand the process of the discretization of hyperbolic equation. Yeah. So now you go here. This is a solution. You need to find 8 points. U11, U21, U31, U41, U12, U22, U32, and U42. All the corners, okay, you have 3 boundary conditions. Okay. Okay, number 1, number 2, and number 3 is given in the question. All right. So when you do a discretization, okay, when you do a discretization, what you get? You get I equal to 1, j is equal to 0. You put at the star function, okay, u11 because j is equal to 1 kan. The rest is depend on j equal to 0 and j equal to negative 1. Be careful when you get the value ui negative 1. That is a corners. There is a corners that is a given in the boundary. So find the boundary, go to the question, find the boundary when I is equal to 1, j is equal to negative 1, it will be replaced to I equal to 1, j is equal to 1, alright? Because of the condition at the boundary. So you will get U11 is just insert the value. U10 is a boundary condition, U20 is a boundary condition. So you solve direct, or we call as a explicit direct. Go, because the value of U10, okay, U20, you get from the boundary condition and initial condition. Here, you get from the initial condition. Okay, so now you move to I equal to 2, j equal to 0. So you will get U21. Refer to the point. Okay, refer to the point. All right, why you need to refer to the point? Because, okay, we draw already the graph, kan? We draw already the graph to where we know where is a U21. It's depend on the initial condition U20, okay, U30, U10. All right, so put the value inside the linear system. All right, even though there is a 5 point, but the difference with the elliptic, you don't have the boundary condition. All right, and then you solve using the implicit, but here you are solve using explicit. Yeah, explicit. All right, so you can get U21 is equal to the value is 0.2265 divided by 2. You get a number for every point you want to find. How many points? 8 points. And then next is u is equal to I equal to 3 and j is equal to 0. So means that you need to find u31. Where is the u31? Is a second time step. Okay, where is to find u32? Is the last time step. Okay, it's a last time step. So you need to repeat to I equal to 3, I equal to 4. All right, I equal to 4. All right, and then I is equal to 1 again when you want to go for the next step. All right, how many points for the first step? 4 points. The second step, another 4 points. All right, so you will get u31 is equal to put inside to the star function. All right, okay, so let's refocus here. Okay, we can see here you move to I equal to 4. You move when I equal to 1, 2, 3, 4. J is equal to 1. When j is equal to 1, j plus 1 is j is equal to 2. All right. So you go to the 4 point, I equal to 1, I equal to 2, I equal to 3, I equal to 4. So you can get the wave at the second time step. Just now you have the wave at the first time step. So that the grid move because of the time step, because you increase y. Alright. So now we move, alright. Do fast. I hope you can do in 20 minutes. Okay. And then you can directly draw the graph of the two time step when j is equal to 1 and j equal to 2. Alright. So this is your aim, direct method for the hyperbolic equation to find the two waves based on the two time step, based on the two types of y. Y equal to 0.1 and y is equal to 0.2. Alright. So now if you go to the hyperbolic equation, okay, I hope that you also need to implement 3 steps. So my question here, what the 3 process, okay, to solve hyperbolic equation. All right, so to solve this problem, don't worry because we always implement. The first is you need to know the boundary condition and initial condition. Put in the graph, okay, the left, the right, and the left, the down, the above, and the up. All right. So, and then where is the solution? Inside the boundary, or there is no boundary at the above one when y equal to 0.2. All right, the last one, I is equal to 2. And then where is the point? This point depends on the boundary condition? Yes. To get U11, you need to know what is a U10, U01, and U12. All right. So what is the value of the U0, U10? Okay, in the boundary. All right, U01 at the boundary, and then U12. U12, you can see here, is also at the boundary or not. Okay, you can go to the chapter again. Okay, is it at the boundary? No, there is not at the boundary. All right, so you can see here. Okay, when we go to the initial condition, boundary condition. Okay, U1. Okay, so you can see here. Okay, I'm stop sharing. All right, I go again to the material, how to discretize. You can see here, U1 x equal to 0.2 and j is a 0.2. So meaning that all the new point U11 is depend on the U j equal to 0, U j equal to 0, U j equal to 0, and U j equal to -1. All right. So you go for the top, top point. All right. So now I'm stop sharing. Okay, I want to share again the process of discretization. Okay, let's we go to the if I can go to the PDF file. All right, so hyperbolic equation. I hope I can share you the hyperbolic equation. Yes, I want to focus this note. All right, and go to the notes. Right, so you can see here the hyperbolic equation. The solution is a direct method. And then the star function. You can see star function. I put in view in the zoom. I make it more 200. Okay, visualization, you can see here. Okay, it's too big. I zoom it to 100. Okay, 100. All right, so this is very convenient for you to all right, you go to here. the process of discretization. Where is my star function? My star function here, all right, is depend on the j plus 1. Okay, it's depend on the j plus 1. What is a j plus 1? J plus 1 is a new time step. The top j, this point. Okay, this point is the wave that you need to search. All right. So now, okay, now let's I focus here. You need to solve using direct method or explicit method. All right, because you have to know all the j. For example, okay, to find the grid. Okay, let's say we go to the PDF file again to get the come on. All right, so to get the okay, let's we go to the this one is very important, yeah, the graph. To get the U12 is depend on the U11, U21, U01 and U10. So it's the boundary. To get the U31 is depend on the U20, U30, and then U41, U31. Okay, it's depend on the previous time step. Okay, this one is depend on the U3 negative one. All right, so to get U31 is depend on the U uh, 20, U30, and then U40, and the rest is the last one is U3 negative one. Right. To get U22 is depend on the U21, U12, U31, and U20. All right. So meanings that all the point is already got. Okay, to get the new time step for the wave. All right, new time step is a U22. So because here, okay, elliptic, the new point is depend on the previous time step, where the previous time step is already calculated, or at the boundary condition, All right, so now I want you to, I want to meet you, okay? I want to meet you at the quizzes. I want you to answer my question, all right? I want to share, okay? I hope I can practice this one, all right? I hope I can start, all right? And then I hope I can give you, okay, wait now. Okay, it's very loud here. Okay, I want to back again. All right, I go to uh, share. Okay, my practice here. Okay, right. All right, I go to this one. Okay, I I go to your okay. I go to the link here. All right, so you can click the link. Go and click the link, or I can send to your telegram, okay, or somebody can send to the telegram. You may start, okay, you may start to answer my quiz, a simple quiz. Don't worry, okay, we are using a simple quiz here. All right, so let's we go. Okay, let's we go. We can start now. And stop sharing and go to the quiz. All right, stop sharing, go to the quiz. Okay, the same time I want to find your, okay, the attendance group. All right, let's go. Okay, you can answer my question very fast.